2 faint red dots. That is all they were, 2 pinpricks of light sitting a hair's width apart, glowing only in the reddest wavelengths the most powerful telescope ever built can see, floating over the most famous picture in all of cosmology. And by every test astronomers have trusted for 30 years, those 2 dots were the most distant objects ever recorded. Light from the first 100 million years after the beginning of time, older than anything any telescope has ever shown us. Older than the first stars were supposed to be. The team that found them could have announced a record that would rewrite the entire story of how the universe grew up. Instead, they did something far stranger. They said nothing. They waited a full year, pointed the telescope at the exact same patch of sky again, and watched to see whether the 2 dots would move, because a galaxy at the edge of time cannot move, and what these 2 turned out to be is hiding closer to Earth than almost anything else in that image, and by the end of tonight it is going to quietly take apart the line you thought separated our own galaxy from the edge of everything. Get comfortable. If you're the kind of person who enjoys watching a clean, certain line slowly dissolve, a quick like and subscribe helps this channel reach more curious minds like you. Because by the end of this, the boundary between the near and the far will never look quite so solid again. Now let's slowly settle into the dark. On the night of January 20th, 2025, in a control room far from almost everyone whose life this story will eventually touch, a short sequence of commands finished its slow climb out to a spacecraft parked 1.5 million kilometers from Earth. The spacecraft was the James Webb Space Telescope, and on that particular night it had been told to do something it does very well and very rarely gets to do at this depth. It was told to turn its 18 golden mirror segments, all at once, in a single coordinated motion, and to point them at a small and unremarkable patch of sky in the southern constellation Carina. The patch of sky was not, in fact, unremarkable. It was the location of one of the most important pictures in modern cosmology, an object that has for almost 20 years served as the most direct piece of visual evidence we have that most of the universe is made of something we cannot see. Astronomers call it the bullet cluster. It is a place where, in 2006, a team led by Douglas Clow used the bending of light and the glow of X-rays to show that when 2 enormous clusters of galaxies collided, the mass and the visible gas ended up in 2 different places. The gas, slowed by the crash, piled up in the middle. The mass, traced by the way it warped the light of everything behind it, had sailed straight through and kept going. You cannot make that picture work without adding something invisible, something that holds the galaxies together and does not care about the collision at all. If someone ever asks you to prove that dark matter is real, the bullet cluster is the image you point to. There is something else about the bullet cluster that matters for the story we're about to tell, and it is quieter than the dark matter. All of that mass spread across the collision bends the light of whatever sits behind it. It magnifies distant galaxies that would otherwise be far too faint to notice. It stretches their images into thin arcs and smears of light that a careful astronomer can read. In other words, the bullet cluster is a lens. It is one of the best natural telescopes in the sky. So when you want to look for the very first galaxies, the ones that formed in the first few 100 million years after the beginning, the bullet cluster is one of the natural places to aim. The cluster does some of the magnifying for you, for free. The program running on Webb that night had a name and a number, the way these things do. It was General Observer Program 4598, and its title was, fittingly, A Silver Bullet for Dark Matter. It was led by an astronomer named Marusa Bradak at the University of Ljubljana, working with colleagues including Marcin Sawicki at St Mary's University in Halifax. The plan was to use the cluster as a lens and to photograph the field behind it at very great depth, in 8 separate infrared filters, each one tuned to a slightly different slice of colour. The filters ran from about 9/10 of a micron, near the edge of what the human eye could almost recognise as deep red, out to 4 44/100ths of a micron, well into the infrared, far past anything you could ever see. Each filter stared for roughly 6,400 seconds, a little under 2 hours. By the time the night was over and the mirrors had swung back to rest, the deepest infrared image ever taken of the bullet cluster was sitting in the spacecraft's memory, waiting for its slow trip home. Let yourself be there for a moment, out where the telescope floats. There is no sound, of course, and no up or down, Only the great sunshield spread beneath the mirror like a kite the size of a tennis court, holding the heat and light of the sun on one side so that the other side can grow colder than almost anything in the solar system. The mirror is a honeycomb of gold-coated hexagons, 18 of them, each one adjusted to a fraction of the width of a wavelength of light, all working together as a single eye. On this night, the whole assembly turns, slowly and precisely, until it is looking back along a line that passes through the bullet cluster and out toward the beginning of time, and then it simply holds still and stares. For nearly 2 hours in each filter, photons that have been travelling for most of the history of the universe fall, one at a time, onto the detectors and are counted and are remembered. There is nothing dramatic to see in the moment. There is only a machine in the dark, patiently gathering light. The drama comes later, days later, when the numbers reach Earth and someone opens the image and finds 2 red points that should not be there. And that is exactly what happens. A few days later, when the processed images reached the science team, almost everyone looking at them was hunting for the same thing. They were looking for galaxies at the very edge of cosmic time, the ones the lens was supposed to reveal. And most of the field behaved exactly the way it was supposed to. There were background galaxies, dozens of them, some bright and some faint, showing up across many filters from the bluer ones to the redder ones. There were foreground stars belonging to our own Milky Way, easy to pick out because they shine in every filter at once. There were the ordinary chores of the work, hot pixels to mask, small imperfections to clean, and then, in one corner of the field, about 12.8 arcseconds apart from one another, there were 2 small, faint red points of light that did not look like anything else in the picture. If it has been a while since you stood under a truly dark sky, and you're trying to picture 12.8 arcseconds as some dramatic gap, let me shrink it for you. 12.8 arcseconds is about the width of a single human hair held out at arm's length. The 2 points sat that close together, near enough that they might be related or might simply be a coincidence of line of sight. They were both extremely faint, and they were both completely absent from the bluer filters. They did not appear in the blue, they did not appear in the green or the near-infrared. One of them, later given the catalogue name Bullet BD2, only began to show up faintly in a filter centered on 2/7700ths of a micron, and then grew brighter as the wavelengths got longer. The other, later named Bullet BD1, did not appear at all until a filter at 3/5600ths of a micron, and then brightened sharply by the reddest filter of all. In the language of the field, these 2 objects were dropouts. They had dropped out of the shorter wavelength images entirely, and only revealed themselves in the reddest light. And if dropouts behave the way dropouts have behaved for 30 years, then that pattern means something very specific about how far away a thing is. This is the moment where the people staring at the first images of the bullet cluster allowed themselves a particular and very careful kind of hope. 2 faint red points in the field of the most powerful natural lens in the sky, faint the way the most distant galaxies are faint, red the way light gets red when it has been stretched across almost the entire history of the universe. If you took the pattern at face value and read them as galaxies, one of them would sit at a redshift of about 30 and the other at a redshift of about 20. And those are not ordinary numbers. A redshift of 30 would mean you were looking at light that left its source when the universe was only about 100 million years old. A redshift of 20 would mean about 180 million years. Both of those are older, deeper, further back than any galaxy anyone has ever confirmed. The team knew what they were holding. They also knew the oldest rule in this kind of work, the one every astronomer learns early and never quite stops hearing. Extraordinary claims require extraordinary evidence, and so, instead of doing the thing that would have made headlines, they did something much harder and much quieter, something that would take a full year and a second journey back to the same patch of sky. Before we follow them there, though, we need to slow down and understand the method itself. We need to understand how a missing colour becomes a measure of distance, why it has worked so reliably for so long, and what single hidden assumption connects a faint red dot to the edge of the observable universe. Because the strange thing that is about to happen in this story is not that the method failed. The method worked perfectly. The 2 dots really were dropouts. They really did have the sharp break that distant galaxies have. The trouble is that something else, something no one at the eyepiece was thinking about that night, makes the very same mark, in the very same colours, and hides in plain sight while doing it. The team had a decision to make, and it is worth sitting with how tempting the easy version of it was. Two faint red points had appeared in the deepest infrared image ever taken of the most famous dark matter picture in the sky. They carried the exact signature that 30 years of astronomy had taught everyone to read as distance. They sat behind a powerful lens that could plausibly boost the light of something impossibly far away into view. Every box you would want checked was checked. If they had simply written the paper, if they had announced the discovery of galaxies at a redshift of 30 and a redshift of 20, the claim would have travelled around the world in a day. It would have been, in plain language, the most distant objects ever seen by anyone, and the people who found them would have had their names attached to a record for as long as the record stood. They did not write that paper. What they did instead is the quiet heart of this whole story, and it is the part that tends to get lost when a result finally becomes a headline. They looked at two objects that could have made their careers, and they decided they were not yet allowed to believe their own eyes. Because they also knew something that complicated the easy reading, something that had been sitting in the literature for years, gathering weight. They knew that the sharp break they were seeing, the clean drop from invisible to visible across a single step of colour, is not produced only by distant galaxies. There is another kind of object, a far closer kind, that makes an almost identical mark in almost the same colours, for reasons that have nothing to do with the edge of the universe. And the deeper the surveys had gone, the more often that other kind of object had started turning up, wearing the same costume, so the team held the record in their hands and set it down. They applied for time on Webb's spectrograph, the instrument that spreads an object's light into its full range of colours, rather than sampling it in a handful of broad filters. And then they did something even rarer than that. They planned to come back. They arranged, through a separate program, to photograph the exact same patch of sky again, 1 year later, with the same filters and the same exposures, so that they could lay the two pictures on top of each other and look for one specific thing. They were going to look for movement. They were going to look to see whether the two red points had shifted, even slightly, across the sky in the 12 months between the images. Because a galaxy at the edge of the universe cannot move, its light has been travelling toward us for almost the entire age of everything. On the scale of a single year, it is nailed to the sky. But an object close to home, drifting through our own galaxy, would slide, just a little. Just enough if you had the sharpest infrared eye ever built to catch. If they found that motion, the entire meaning of the two dots would flip in a single measurement, from the farthest things anyone had ever seen to something sitting right here in our own neighbourhood, hiding among the record breakers. They did not know yet which answer the sky would give them. That was exactly the point. They had trained themselves not to decide in advance, and so they settled in to wait, which in modern astronomy is a much harder discipline than it sounds, because the temptation to be first is enormous, and the cost of being wrong in public is worse. They wrote two versions of the analysis, one assuming the objects were galaxies and one assuming they were something local, so that whichever way the data broke, they would be ready. They gave a brief talk at a conference in early 2025, in which they mentioned the candidates and pointedly declined to say what they thought the candidates were, and they watched the calendar. I want to slow down and honour that choice, because it is easy to skate past and it is really the moral centre of the whole story. Put yourself in their place. You have spent years building toward moments like this. You have two objects that carry the exact signature of the most distant things anyone has ever seen, sitting behind the most famous lens in the sky, endorsed by a method that has been right thousands of times. The paper would almost write itself. Your name would be attached to a record for as long as the record stood, and records like this do not come along in most careers. Every incentive in the modern scientific world, the pressure to publish, the race to be first, the way attention flows to the biggest claim, is pulling you toward the keyboard. And you look at all of that, and you set it down, because you know something the incentives do not care about. You know that the bigger the claim, the more ways it can be wrong, and you know there is a specific documented way this exact kind of claim has gone wrong before. So you choose to be slow. You choose to spend a year in uncertainty rather than a day in the headlines, because you would rather be right in the end than first in the moment. That is not caution as timidity. That is caution as a kind of courage, the willingness to hold a wonderful possibility loosely enough that the truth can still take it away from you. It is the quiet heart of how science actually works, and it almost never makes the news, precisely because doing it right means there is nothing to announce for a long time. There is a phrase that began to circulate quietly inside the team during this period, half a joke and half a real suspicion, And it is worth introducing now because it is going to come back more than once before we are done. The phrase was this: the most distant thing in the picture might also be the closest. Until proven otherwise, the two dots could go either way. They could be the dawn of cosmic time, or they could be something drifting past us at a distance we could practically walk to, on the scale of the universe. Nobody knew. And rather than resolve that discomfort by choosing the exciting answer, the team chose to live inside the discomfort for a year. To understand why that discomfort was justified, and why patience was not just caution, but wisdom, we need to leave the control room for a while and understand the tool that produced the mystery in the first place. We need to understand how a telescope can look at a smear of red light and read a distance off it, a distance measured in billions of years, without ever moving from its parking spot. The method is elegant, it is old by the standards of this field, and it has been right thousands upon thousands of times. Its reliability is exactly why the two dots were so seductive. So before we return to the two red points and the year of waiting, let us go back 3 decades, to a short paper that quietly changed what a telescope could be used to find. In 1996, an astronomer named Charles Steidl and 4 colleagues published a short letter in a research journal that has since been cited thousands of times, and that quietly rebuilt what was possible in the study of the distant universe. The idea in it was almost embarrassingly simple to state. Take a picture of the same patch of sky through several different colour filters, spanning the ultraviolet and the visible. Then look for objects that are bright in some filters and completely missing in others. Specifically, look for an object that vanishes below a certain colour and appears cleanly above it. That sudden step, that cliff in the object's light, is the signature of a very distant galaxy. And the reason it works comes down to the single most common thing in the universe, which is hydrogen. The early universe was almost entirely hydrogen and helium, and even now, more than 13 billion years later, hydrogen is still by far the most abundant ordinary matter there is. Hydrogen atoms scattered thinly through the space between us and any distant galaxy do something very particular to light. They greedily absorb any photon whose wavelength is shorter than a specific threshold, a wavelength of about 912 angstroms, which is the exact amount of energy it takes to tear the single electron off a hydrogen atom. Light bluer than that threshold gets swallowed. Light redder than that threshold passes through. And so, when you look at a galaxy from very far away, its light carries a sharp cliff. Above the threshold, the galaxy shines more or less as it should. Below the threshold, the galaxy goes dark. There is a step in the spectrum, a place where the brightness suddenly falls off, and that step is called the Lyman break. For a galaxy close by, that break sits in the ultraviolet, in a part of the spectrum that most telescopes on the ground cannot even see. But the universe is expanding, and expansion stretches the wavelength of every photon travelling through it. The farther away a galaxy is, the longer its light has been on the road, and the more that light has been stretched. So the break, which starts in the ultraviolet, gets dragged toward longer and longer wavelengths as the distance grows. At a modest distance, it slides into the blue edge of the visible. Farther out, it moves into the red. Farther still, it crosses out of visible light entirely and lands in the infrared. At a redshift of 7, the break sits around 7,300 angstroms, at the red end of what the eye can manage. At a redshift of 14, it has moved to roughly 14,000 angstroms, well into the near-infrared. At a redshift of 20, it lands near 19,000 angstroms. At a redshift of 30, it reaches about 28,000 angstroms. And at every one of those distances, the result is the same in kind. There is a wavelength below which the galaxy is essentially gone, and above which it returns. If you take pictures through a set of filters that bracket where the break should be for a given distance, and you find an object that disappears in the filters below the break and appears in the filters above it, you have almost certainly found a galaxy at that distance. You have found it without a spectrum, without spreading its light apart, just from the pattern of which filters see it and which do not. Steidl's original work applied this trick to galaxies at a redshift of around 3, where the break sits in the near-ultraviolet, and those galaxies came to be called Lyman break galaxies. The technique became the workhorse of distant galaxy hunting for the next decade and more. The Hubble Space Telescope's famous deep fields, taken in the 1990s and again in the 2000s, were full of dropout candidates found this way. Survey after survey pushed the method to higher redshifts, into the optical, and then into the near-infrared, cataloguing first dozens, then hundreds of these galaxies. By the time the James Webb Space Telescope launched in December of 2021 and began returning science data in the middle of 2022, the dropout method had been validated on thousands of galaxies across a range of distances that no earlier generation of astronomers could have reached. It works. When you find a clean dropout, you are, overwhelmingly, finding a galaxy. It is worth pausing on how much trust had been built into that sentence, because the trust is exactly what made the two dots so convincing. Think of what it means to validate a method thousands of times. Every one of those thousands of dropouts was a small act of faith that paid off. An astronomer would find an object missing in the blue filters and present in the red, would predict from that pattern alone a distance measured in billions of years, and then, when a spectrum could finally be obtained, the spectrum would confirm it. Again and again the prediction held. The break was where the filters said it would be. The galaxy was as far away as the colours implied. Over 3 decades, across telescope after telescope, the method earned the kind of reliability that lets you stop double-checking, the way you stop checking whether the sun will rise. This is the reliability the Bullet team was leaning on when they looked at the 2 red points. They were not being naive. They were trusting a tool that had almost never let anyone down, and the tool had been extended right up to the edge of the possible by Webb itself. Consider what it takes to catch a galaxy at a redshift of 10 or 12. The light left that galaxy when the universe was a few 100 million years old. It has been travelling ever since, stretched longer and longer by the expansion of space, until the ultraviolet glow of hot young stars has been dragged all the way into the infrared. To catch that light, you need a telescope cold enough and sensitive enough to see a faint infrared whisper against the dark, and Webb is exactly that. A machine chilled and shielded and parked in the cold far from Earth, precisely so that it can hear those whispers. When Webb turned that capability on the deep sky, it began finding dropouts at distances that had been pure speculation a decade earlier. Each one was a small triumph of the method. Each one deepened the confidence. So by January of 2025, when 2 dots appeared in the reddest filters over the Bullet cluster, the entire weight of that history was pressing toward a single conclusion. These are galaxies. They are the most distant ones yet. The method says so, and the method is almost never wrong. That pressure, that 30-year accumulation of being right, is precisely what the team had to resist. Webb extended the reach of the method further than any instrument before it, and it did so in the most natural way. Webb is built almost entirely for the infrared. Its detectors are sensitive from a little below 1 micron out to nearly 30 microns, which means it can see the Lyman break for galaxies at distances no previous telescope could touch. Its near-infrared camera carries a set of broad filters that astronomers recognized immediately as a nearly perfect toolkit for dropout work. Each filter catches the break at a different redshift, stepping outward in distance as you move to redder filters. The filter at 9/10 of a micron catches galaxies dropping out around a redshift of 7. The next catches redshift 8 or 9. Others reach 11, then 14, then around 20, and the reddest filters of all could, in principle, catch a dropout at the very edge of the observable universe, a galaxy from the first faint chapter of cosmic history. So when the Bullet cluster team looked at their images and saw 2 faint red points that appeared only in the longest filters, they were looking at exactly the kind of object this method was built to find. The signal was clean, the break was sharp, the colours were consistent with the Lyman break sitting right where it should for objects at the edge of time. By every standard the technique had used for 3 decades, and by every test it had passed on thousands of real galaxies, those 2 dots had earned the right to be considered candidates for the most distant objects ever observed. But the team also knew the one thing the method could not do on its own. It could not, from broad filters alone, tell the difference between the Lyman break of a galaxy at the dawn of time and a completely different kind of mark, made by a completely different kind of object, that happens to fall in the same colours. To see why that matters, we first have to understand just how far back a redshift of 30 really reaches, and why a galaxy at that distance would not simply be a record. It would be a problem. To feel the weight of what these 2 dots would mean, you have to hold the calendar of the universe in your mind, and it is a calendar with very specific dates on it. The universe is about 13,787,000,000 years old. That figure comes from the Planck satellite's careful measurement of the oldest light in the sky, and it has held steady across several independent methods for more than a decade now. It is one of the most precisely known numbers in all of science, pinned down to better than 1 part in 500. So when we talk about the age of everything, we are not waving our hands, we are reading off a clock we trust. The beginning, in this picture, is the moment when the universe was impossibly hot and impossibly dense, the moment from which time as we measure it began to run forward. For the first few 100,000 years, the universe was a glowing fog, a plasma of loose protons and electrons and light, so thick that no ray could travel any real distance before being scattered. Light and matter were locked together in a bright opaque soup. Then, about 380,000 years in, the universe cooled just enough for the protons and electrons to settle into neutral hydrogen atoms, and suddenly the fog lifted. Light was free to travel in straight lines for the first time. That first release of light is still arriving today, stretched by all the expansion since into a faint microwave glow that fills the whole sky, cooled from thousands of degrees down to less than 3 degrees above absolute zero. We call it the cosmic microwave background, and it is the earliest thing we can see directly. After that flash came a long quiet darkness that astronomers simply call the Dark Ages. The universe was full of neutral hydrogen, but there were no stars yet, nothing burning, nothing shining. It was a cooling expanse of gas waiting for gravity to do its slow work. The first stars are thought to have switched on somewhere between 100 million and 200 million years after the beginning. They were, in the models, enormous and hot and short-lived, built entirely from hydrogen and helium because nothing heavier existed yet. And the first true galaxies, the first gatherings of many stars bound together, are believed to have assembled somewhere between 300 million and 500 million years after the beginning. That is the era we usually mean when we talk about the cosmic dawn. Try to picture that darkness, because it is important to feel how empty the early universe really was, and how strange it would be to find anything bright inside it. For tens of millions of years after the fog lifted, there was no light source anywhere. The universe was filled with cooling hydrogen, spread thin and even, slowly gathering into faint threads and knots under the patient pull of gravity. There were no stars to see by, no galaxies, no colour, only a dim, expanding darkness getting colder by the century. If you had been there, floating in that gas, you would have seen nothing at all, not because there was a shortage of matter, but because nothing had yet caught fire. It took 100 million years or more for the first knots of gas to grow dense enough at their centres to ignite, and when they did, they came on as a scattering of brilliant, lonely stars, blazing in an otherwise empty dark, each one an island of light in an ocean that had never known any. Those first stars did not gather into galaxies for a long time yet. They lived and died mostly alone, seeding the darkness with the first heavy elements, the first carbon and oxygen and iron ever to exist, cooked in their cores and scattered by their deaths. This is why a bright assembled galaxy at a redshift of 30 would be such a problem. At that distance, we would be looking at the universe when it was only about 100 million years old, right at the very edge of when the first individual stars are thought to have appeared, long before there was time to gather them into anything you could call a galaxy. There should be, at most, a few scattered points of early starlight, far too faint to see across that gulf, even with a lens boosting them. A whole galaxy, bright enough to catch, would be an object out of sequence, arriving before the universe had finished making the conditions for it. That is the specific strangeness the 2 dots seem to promise, and it is the specific strangeness that made the team so careful. A record is exciting. A thing that should not exist yet is either a revolution or a mistake, and revolutions are rare while mistakes are common, so wisdom leans, at least at first, toward the mistake. Now set the 2 dots against that calendar. The current record for the most distant galaxy anyone has actually confirmed, with a real spectrum and not just a dropout pattern, is an object called Jade's GSZ14, seen at a redshift of about 14 1/3. We are looking at it as it was when the universe was roughly 290 million years old. Sitting just behind it is another candidate at a similar distance. These confirmed early galaxies are already, by the standards of the models astronomers had before Webb, a little surprising. They are brighter and more plentiful than the older predictions expected, and there has been real, healthy argument about why. But they are within reach of explanation. They sit inside the window where galaxies are allowed to exist. The dots do not. Bullet BD2, read as a galaxy, would sit at a redshift of about 20, which places it around 180 million years after the beginning. That is more than 100 million years earlier than the confirmed record. It lands in territory where galaxy formation models, stretched as far as they can honestly go, simply do not have a comfortable way to make something bright enough to see, even with a lens boosting the light. And Bullet BD1 is worse. At a redshift of about 30, it would sit around 100 million years after the beginning. That is the era of the very first individual stars. There should not yet be a galaxy there at all. There should be, at most, scattered points of light, lonely early stars a few hundred to a few thousand times the mass of the Sun, sprinkled across an otherwise dark sky of neutral hydrogen. Anything bright enough to be caught by a telescope, even the most sensitive one ever flown, even with a natural lens in front of it, would be something that no current model of how galaxies grow can comfortably produce. Sit with what that would have meant. If the team had been able to confirm these two objects as real galaxies at those distances, the paper would not have been merely a record. It would have broken the standard model of how the first structures in the universe came together. Every theory of early galaxy formation would have needed to be rewritten. Either the first stars formed far more efficiently than any simulation suggests, or there was some entirely new piece of physics at work, or some unknown mechanism was building bright structures in the first 100 million years of cosmic time. The implications would have been enormous, and the headlines really would have written themselves. This is exactly the reason the team could not let themselves believe it. The bigger a claim is, the more ways it can be wrong, and the more carefully it has to be tested before it is allowed out into the world. The history of cosmology is full of results that looked dramatic and turned out to have ordinary explanations. A famous announcement in 2014 of ripples in space-time from the birth of the universe turned out, on closer inspection, to be mostly dust in our own galaxy. Hints of new particles and unexpected signals have surfaced and dissolved more than once, revealed in the end to be quirks of the instrument or the calibration. Anyone who has spent even a few years in this field develops an instinct for the kind of result that demands patience before publication. The Bullet Cluster team had that instinct in full, and they had, on top of the general caution, one very specific worry with a name attached to it. They knew that cold, failed stars in our own galaxy could counterfeit the colours of a distant galaxy in exactly this kind of imaging. And they knew that this was not a hypothetical fear, because it had already happened, publicly, to another team with another object only a year before. Its nickname was Kappa Tauro, and it was sitting in the back of every careful astronomer's mind. To understand why the team waited, we have to meet it. To really understand why the Bullet Cluster team chose patience over a headline, we need to spend some time with the object that had already put the whole field on edge. We need to understand what had happened to the previous most distant galaxy candidate, and why the lesson of that case was sitting quietly in everyone's thoughts by the time the two red points showed up in the bullet field. The object had a formal catalogue number, dull and precise, but it had also earned a nickname, the way objects do when a community keeps coming back to them. The nickname was Kappa Tauro, after a small, obscure mountain, the kind of sharp little peak you notice and remember. And Kappa Tauro was, for a while, the most extreme distant galaxy candidate anyone had ever found. Kappa Tauro turned up in one of the early large web surveys, a program that had imaged a small patch of sky in the constellation Bootes at great depth in many filters. Buried in that survey's longest wavelength images was a single faint red point of light, picked out during a careful reanalysis by a team led by an astronomer named Mara Gandolfi and her colleagues. The object was faint but real. It was absent from every filter below about 3.5 microns, and then, between one filter and the next, its brightness leapt by more than a factor of 15, across less than an octave of colour. It was the sharpest dropout in the entire survey. If you read that pattern the standard way, as the Lyman break of a distant galaxy, it implied a redshift of about 32. The universe at that distance would have been only about 90 million years old. That is 200 million years earlier than the confirmed record. It is well inside the era when, according to every model calibrated against everything we had seen before, individual stars might exist, but galaxies bright enough to be seen across that distance simply should not. Gandolfi and her collaborators faced the same choice the Bullet team would face 2 years later, and they handled it with the same care. They could have announced the most distant galaxy ever found. Instead, they wrote the paper honestly, laying out not one interpretation but 3. The object might be a record-breaking galaxy at a redshift of 32. Or it might be a much closer galaxy, wrapped in dust, at a far more modest distance, its light reddened not by the expansion of the universe, but by the grime of its own interior. Or it might be an ultra-cool failed star in our own galaxy, a brown dwarf, whose cold atmosphere happened to counterfeit the break of a distant galaxy. They titled the work in a way that admitted the ambiguity right up front, and they made it clear that follow-up was needed before anyone could say what Capitaro really was. The follow-up came over the next year. The team gathered more imaging, reanalyzed the colours, consulted specialists in the spectra of the coldest failed stars, and even explored an exotic fourth possibility, that the object might be the explosive death of a very massive early star, a kind of detonation that leaves no remnant behind, seen at a middling distance and stretched out in time by the expansion of the universe. By the time the fuller analysis appeared, the nickname had taken hold and the title had grown starker, framing the object plainly as a puzzle. The paper laid out the case for and against each interpretation in careful detail. The galaxy reading was technically possible, but demanded a brightness that no model could comfortably supply. The failed star reading fit the colours well, suggesting an extremely cold object somewhere between 100 and a couple thousand light-years away. The exploding star reading was speculative but physically motivated, and crucially the paper did not declare a winner. It laid out the evidence, noted that the galaxy interpretation was actually the worst fit of the three by the numbers, and called for two specific tests that could settle it. One was a beta spectrum, the other was a measurement of motion. That second test is the one that matters most for our story, so let me make it concrete. If Capitaro is a galaxy at the edge of the universe, it cannot move across the sky in any measurable way. Its position is fixed. But if it is a cold, failed star a few hundred light-years away, drifting through our own galaxy, then over a few years it should shift, slightly, against the background of truly distant objects. The team had assembled a baseline of a little over 2 years from combining several observations, and from it they could say that the object had not moved by more than about 137 thousandths of an arcsecond per year. That sounds like a tight limit, and it is, but it was not tight enough. A failed star anywhere from about 100 to nearly 2,000 light-years away could sit comfortably under that limit and still be drifting, and a genuinely distant, motionless galaxy would also sit under it. The measurement, in other words, was consistent with both answers. It could not choose. What the field needed was a motion measurement far more precise enough to catch a shift of just a few thousandths of an arcsecond, and that would require going back for a second look with a long enough gap in between. It is worth lingering on that third interpretation of the exploding star, because it shows how many ways a single faint red dot can lie to you, and because it is the strangest of the possibilities. A very massive early star, one built from pure hydrogen and helium with no heavier elements to complicate it, can die in a particular and violent way. If the star is heavy enough, somewhere between about 140 and 260 times the mass of the Sun, the core gets so hot that its light begins spontaneously turning into pairs of particles, matter and antimatter, conjured directly out of energy. That conversion robs the core of the pressure that had been holding the star up against its own gravity. The star begins to collapse. The collapse triggers a runaway thermonuclear fire, and the entire star detonates, leaving nothing behind at all, no remnant, no core, just an expanding cloud and a fading light. It is a kind of death that has been predicted in theory for decades, but never once been confirmed by direct observation. And here is the twist that matters for our story. Such an explosion, seen at a middling distance and stretched out in time by the expansion of the universe, could produce a slow rise and fall of light in exactly the reddest filters, and could, for a single snapshot, look very much like a dropout. So Capitaro carried not 2 but 3 possible identities, and each one was, in its own way, spectacular. A record galaxy, a cold failed star, or the first exploding giant of the early universe ever caught in the act. The team that studied Capitaro laid all 3 side by side and refused to crown a winner. They did note, honestly, that the galaxy reading was actually the poorest fit of the 3 by the numbers, and that the failed star and exploding star readings were roughly comparable, and they pointed, as the bullet team would later point, to the 2 tests that could finally decide it, a better spectrum and a measurement of motion. Their existing look for motion, drawn from a baseline of a little over 2 years, could only say that the object had not moved by more than a certain modest amount each year, a limit loose enough to be consistent with a failed star anywhere from 100 to nearly 2,000 light-years away, and also consistent with a galaxy fixed at the edge of everything. In other words, the existing motion limit did not choose. It ruled nothing out. It simply marked the spot where a sharper measurement would have to be made. This was the case study sitting in everyone's mind when Bullet BD1 and Bullet BD2 appeared in the bullet cluster images. The parallel was almost uncomfortable. Two new dropouts, in a different lensed field with similar colours, carrying the same beautiful and treacherous ambiguity. The most distant thing in the picture might also be the closest. That phrase, which had begun as a working suspicion, was starting to feel less like a joke and more like a warning. The Bullet team knew Capitaro's story in detail. They knew about the growing pile of failed stars that had been caught masquerading as distant galaxies in other surveys. And they knew that the only honest way forward was to do exactly what the Capitaro team had called for, but to do it decisively. They would get the spectrum, they would schedule the second look a full year later, and they would measure the motion of their two dots precisely enough that there could be no argument left. But to understand what they were really testing for, we have to understand the imposter itself. We have to understand what kind of object can sit in our own galaxy and wear the face of the cosmic dawn. Here is the coincidence at the centre of this entire story, the thing that makes it possible at all, and it is worth stating slowly because everything else hangs on it. Two completely unrelated kinds of objects, in two completely unrelated parts of the universe, driven by two completely unrelated pieces of physics, leave the same fingerprint in our best broadband images. One is a galaxy at the very beginning of cosmic time, billions upon billions of light-years away. The other is a cold, failed star drifting through our own galactic neighbourhood, close enough that its light reaches us in a couple of thousand years rather than a couple of billion. And from the outside, in the kind of pictures Webb takes, the two look almost exactly alike. We have already met the first fingerprint. For a distant galaxy, the mark is the Lyman break, the cliff carved into its light by all the neutral hydrogen between it and us, stretched by the expansion of the universe into the infrared. Below a certain colour, the galaxy is dark. Above it, the galaxy returns. That is the pattern the dropout method is built to catch, and for a galaxy at a redshift of 20 or 30, the cliff lands right in the reddest filters Webb carries. Now let me show you the second fingerprint, the one that has nothing to do with distance at all. A brown dwarf is a strange kind of object, and we will spend real time with it later, but for now you only need the essentials. It is, in the simplest terms, a failed star. It formed the way a star forms, from a collapsing cloud of gas, but it never gathered quite enough mass to ignite steady hydrogen fusion in its core. So instead of switching on and burning for billions of years, it simply glows with leftover heat and slowly, slowly cools. The very coldest of these failed stars, a category astronomers label the Y-class, have surface temperatures between about 250 and 500 degrees above absolute zero. At those temperatures, the object is far too cold to be dominated by the glowing gases of a real star. Its atmosphere is ruled by molecules. Methane, water vapour, ammonia, and other familiar compounds float in its air, and each of them absorbs light at particular wavelengths, carving the object's spectrum into a distinctive shape. The important part, for us, is what that shape looks like in Webb's broad filters. In a cold brown dwarf, the combined absorption of water and methane cuts deeply into the light at wavelengths shorter than about 3 or 4 microns, dimming the object severely in the near-infrared. But at slightly longer wavelengths, between about 4 and 5 microns, the absorption bands relax, and the object shines through far more brightly. The result is a spectrum that stays faint through the shorter filters and then rises sharply in the reddest ones. And that rise, to the standard tools astronomers use to hunt for distant galaxies, looks almost exactly like a Lyman break. It sits in the same colours, it has the same general shape. In low-resolution imaging, where you're only sampling the light in a handful of broad filters, rather than spreading it into a fine spectrum, the two are, for practical purposes, the same mark. This is not a flaw in the method. I want to be careful here, because it is easy to hear this story as the dropout technique being exposed as broken, and that is not what happened. The method does exactly what it was designed to do. It finds objects with a sharp break in the right colours. The problem is deeper and stranger than a broken tool. The problem is that the universe contains two entirely different kinds of objects that produce that break for entirely different reasons, and by an accident that nobody arranged, the two reasons land in the same place. The hydrogen blanketing of a galaxy at the dawn of time and the methane and water absorption in the atmosphere of a nearby failed star are not similar processes. They share no mechanism. One operates on light that has crossed almost the entire universe. The other operates on light from an object practically next door. They have nothing in common except that they happen to bend the light at the same wavelengths. They are, in a sense, accidental homonyms. The universe is speaking two completely different words, and in the low-resolution language of broadband colour, the two words sound identical. And here is the part that had been quietly raising the stakes for a couple of years before the bullet dots appeared. This confusion was not a rare theoretical worry. The deeper the surveys went, the more of these imposters turned up. One team had identified cold failed stars that had been mistaken for a strange new class of distant object. Another had found several more masquerading as record galaxies in the deepest fields. A large survey had turned up a whole handful of them among its candidates. The contamination was real, it was recurring, and nobody yet knew exactly how bad it was, or whether the most extreme distant galaxy candidates ever found were on the clean side of the catalogue or the contaminated side. There is a particular unease that grows in a field when a problem like this starts surfacing, and it is worth describing because it shaped how the bullet team behaved. At first, a single misidentified object looks like bad luck, a one-off, a curiosity. Then a second one turns up in a different survey, and a third, and a small handful in a fourth, and slowly the pattern stops looking like bad luck and starts looking like a property of the data itself. Astronomers began to realize that these cold imposters were not rare accidents, but a standing hazard, sitting quietly in every deep field, waiting to be mistaken for the very thing the surveys were built to find. And the worst part of the unease was not knowing the scale of it. If 1 in 1,000 candidates was a failed star, that was a manageable nuisance. But what if the rate climbed for the most extreme candidates, the redshift 30 dropouts, the record breakers, the ones that generate the headlines? What if the very objects most likely to be celebrated were also the objects most likely to be imposters, precisely because they sat at the extreme edge where the two fingerprints overlap most completely? That was the fear. It was not that the method was useless. It was that the method might be failing most often in exactly the place where being right mattered most. So by early 2025, when 2 perfect dropouts appeared in the bullet cluster field, the community was primed. The people who understood the contamination problem did not look at those 2 red points and feel only excitement. They felt excitement braided with suspicion, the specific suspicion that comes from having watched this movie before and knowing it sometimes ends with a cold local star instead of a distant galaxy. The bullet team was squarely among those people. They knew the growing pile of misidentifications. They knew the cautionary tale of the object that had come before, and they knew that the only responsible thing to do with 2 objects this extreme was to assume, until proven otherwise, that they might be the closest things in the frame rather than the farthest. That assumption is not pessimism. It is discipline. It is the habit of a field that has been humbled enough times to stop trusting its first impression, no matter how beautiful that first impression is. This was the situation the bullet team was standing in. 2 perfect dropouts in a lensed field that the standard method endorsed completely, and a known growing population of nearby objects that could counterfeit exactly that signal. They could have published. They chose instead to apply for a spectrum and to schedule a second look a year out so they could watch for motion. Before we follow them into that year, though, it helps to stop and gather what we know, because the pieces are now all on the table, and the shape they make together is the real subject of this story. Let us step back for a moment and lay the pieces side by side, because we have gathered quite a few of them now, and the picture they make is worth seeing whole before we go any further. This is the halfway point of the story, and it is a good place to slow down and breathe, the way you might pause on a walk to look back at how far you have come before turning to the climb ahead. We have a telescope, the most sensitive infrared eye ever built, parked far from Earth and aimed at the most famous dark matter picture in the sky. We have 2 faint red points of light that appeared in that picture, visible only in the reddest filters, carrying the exact signature that 30 years of astronomy has taught us to read as enormous distance. We have a method, the dropout technique, that is genuinely excellent, that has found thousands of real galaxies, and that endorsed these 2 dots completely. If you trusted the method alone, you would already be writing the press release. you would be announcing the two most distant objects ever seen from a time before galaxies were supposed to exist. And then we have the complication, the thing that keeps the press release in the drawer. We know that the same sharp break can be made by something that has nothing to do with distance. A cold, failed star in our own galaxy, wrapped in an atmosphere of methane and water, produces a rise in the same colours, a mark that the method reads as a Lyman break, but that is really just the chemistry of a nearby object too cool to burn. We know this is not a rare fluke, because these imposters have been turning up again and again in the deepest surveys, and we know from the cautionary tale of Capitauro that the previous most extreme candidate is still sitting unresolved, still waiting for the one test that could tell which kind of object it truly is. So the whole story comes down to a single question, and it is a beautifully clean one. Are the two dots far away or close by? Are they the dawn of time or the neighbourhood next door? And the elegant thing about this question is that there is a measurement that can answer it with almost no room for argument. A galaxy at the edge of the universe cannot move across the sky. Its light has been travelling for nearly the entire age of everything, and on the scale of a single year it is fixed in place, motionless. But a failed star a couple of thousand light-years away, drifting through the disk of our own galaxy at the ordinary speeds that objects move at out there, would shift. Not much. A tiny fraction of an arc-second in a year, a shift you could never see by eye, a shift that takes the sharpest telescope ever made to detect at all, but it would shift. And so the entire mystery, all of this deep time and hydrogen and methane and lensing, collapses down to one simple thing you can watch for. Does the dot move? If it does not move, the team is holding a discovery that would rewrite cosmology. If it does move, they are holding something quieter and, in its own way, even stranger, an object that pretended to be the edge of the universe and was hiding in our own backyard the whole time. There is no third answer. This is the rare kind of question in science that comes with a clean yes or no attached, and the only cost of getting that answer is patience. You have to take the first picture, you have to wait a year, you have to take the second picture, and then you have to lay them on top of each other and look. That is exactly what the team set out to do. They had their first epoch, the images from January of 2025. They had scheduled the second epoch for a year later, through a separate program, timed to land one day past the anniversary, so the gap would be almost precisely 1 year. And in between, they had a spectrum on the way, the spread-out light of the two dots, which might tip the odds one way or the other, even before the motion test arrived. So the year of waiting was not empty. It was full of quiet, careful work, and it was heavy with the suspense that only a handful of people in the world even knew to feel. Notice, before we go on, how much this single clean question has already reshaped the story. We began with something that sounded like a cosmic mystery, the appearance of two objects from before galaxies should exist, and we have narrowed it, step by step, down to a question you could almost put to a child. Are the dots far away or close by? Watch and see if they move. All the grand machinery, the hydrogen and the expansion and the deep time, has funneled into one small, decidable thing. That is often how the best science works. It does not resolve a great mystery by matching it with a great answer. It resolves it by finding the one humble measurement that the mystery cannot survive, and then making that measurement carefully. The Bullet team had found theirs. Now they only had to be patient enough to take it, and patience, as we have seen, was the one thing they had already proven they possessed. So the calendar turned, one slow month at a time, toward the second look. Let us go into that year with them. The spectrum came first. On the night of March 27th, 2025, about 2 months after the first images, Webb spread the light of the two dots apart using its spectrograph in a low-resolution mode, a setting that captures the entire range of the instrument's colours in a single exposure but does not resolve the fine detail. It was the right tool for the job at hand. The team did not need to see delicate individual features. They needed to see the overall shape of each object's light, the location of the break, and the broad signatures that separate one kind of object from another. For two faint dots whose whole question was whether they were distant galaxies or cold nearby stars, the low-resolution spectrum was exactly enough to begin narrowing things down. The spectra came back within a few weeks, and the news was mixed in the most frustrating possible way. The signal was clear. The shape of each spectrum was visible. The wavelength range covered exactly the region where a distant galaxy's break, or a cold star's methane absorption would show itself. And when the team fit the data with both kinds of models, the answer was maddeningly balanced. Either interpretation was consistent with what they saw. The failed star models fit slightly better, by a small margin in the numbers, but not by enough to settle anything. The galaxy models were not ruled out. By the end of that spring, the spectrum had nudged the team's private confidence toward the failed star reading, but only nudged it. If they had been forced to bet, they would have bet on brown dwarfs. But betting is not confirming, and they were not in the business of betting. They needed the motion. So the summer passed, and they waited. They worked on other things, as scientists do, letting the two dots sit in the back of the mind the way an unresolved chord sits in the ear. They watched the wider field, where other teams were steadily turning up more of these cold imposters, and, importantly, showing that Webb really could measure the tiny motions of nearby failed stars over a few years. One group demonstrated a clean detection of exactly this kind, a cold star drifting at a measurable pace across a multi-year baseline, proving that the method the Bullet team was counting on would actually work when their own second epoch arrived. That mattered. It meant the plan was sound. It meant that if their two dots were nearby stars, the motion would be there to find, and if the dots were galaxies, the motion would be flatly absent. Either way, the second picture would speak clearly. Let me make that demonstration concrete, because it is the quiet reassurance the whole plan rested on. Another team had taken a cold failed star, one that had originally been flagged as a possible distant galaxy, and had watched it across a multi-year baseline of Webb images. Over that span, the object had slid across the sky by a small but clean amount, about 20,000ths of an arcsecond per year, a motion that translated to a real sideways speed of a couple hundred kilometers per second, the ordinary pace of an object belonging to the older populations of our galaxy. The object that had once been catalogued as a candidate galaxy at a great distance was, once its motion was measured, unmistakably a local failed star. That result did two things for the Bullet team at once. It confirmed that Webb could measure these tiny motions at all, down to the level they would need, and it confirmed that the whole logic held together, that a moving dot is a nearby dot, and a fixed dot is a distant one, with no middle ground to hide in. The tool worked. The logic was sound. All that remained was to point it at their own two objects and wait for the calendar. So they waited. And waiting, in this kind of work, is its own discipline. It is easy to romanticize the moment of discovery, the number resolving on the screen, but most of science is the long, patient interval before that moment, the interval in which nothing is confirmed and everything's possible, and the temptation to decide early never quite goes away. The team lived inside that interval for a year. They watched other groups find more of these cold imposters, steadily, in field after field. Each new one a small vote for the failed star reading of their own dots, and yet not one of those votes was proof. They read the deepening story of Capitaro, so much like their own, still unresolved. They built and tested their software through the winter, so that when the second images arrived they could act within days rather than weeks. They modelled the errors, calculated the precision they would reach, and confirmed to themselves that the answer, when it came, would not be ambiguous. If the dots were galaxies, the measured motion would land at essentially zero, well inside the noise. If the dots were nearby failed stars, the motion would land at tens of thousandths of an arcsecond per year, far above the noise, impossible to miss. There would be no grey zone. The universe was going to give them a clean yes or a clean no, and all they had to do was survive the wait to hear it. Autumn came, and with it the fuller analysis of Capitaro, the object that had started all of this. Its story deepened without resolving. The weight of the evidence there was also leaning toward the cold star reading, but its decisive motion test had not yet been done, and so it remained officially open, a question mark hanging over the field. The Bullet team read it closely. They saw their own situation reflected in it, and they prepared. Through the winter they built the machinery they would need the moment the second images landed. They wrote the software to line up the two epochs precisely, to register them against the same reference stars, to measure any shift down to a few thousandths of an arcsecond. They modelled the errors they expected. They calculated how precisely they could measure the motion, given the brightness of the dots and the sharpness of the telescope, and the answer was good. If the objects were galaxies, the measured motion would come out at essentially zero. If they were nearby failed stars, it would come out at tens of thousandths of an arcsecond per year, a value far above the noise. There would be no ambiguity left, the result would be decisive. The second images were taken on January 21st, 2026, one day past the calendar anniversary of the first. The telescope returned to the same patch of sky in Carina. The pointing was matched. The filters were the same. The exposures were the same. The gap between the two epochs came out to almost exactly 1 year, 1 3/1000ths of a year to be precise. The data came down within a few days. The pipeline the team had built through the winter began to run. The images were registered against the reference stars. The measurement was performed. Let me slow all the way down here, because this is the moment the whole year had been bending toward. Picture a small office, late on a winter afternoon, the light going blue outside the window. Picture a member of the team, perhaps a graduate student, perhaps a postdoc, sitting in front of a screen with two images open side by side. On the left, the field as it looked in January of 2025. On the right, the same field, 1 year later. The reference stars have been used to lock the two frames into the same coordinate grid, so that anything truly fixed in the sky sits in exactly the same place in both pictures. The two faint red points, the ones that had launched a year of careful silence, are visible in both, and now there is only one thing left to do, which is to look at whether they are in the same place. The person moves the cursor to the position of the brighter dot in the first image. Then they look at where that same dot sits in the second image, a year later, and they measure the gap between the two. Whatever they were feeling in that moment, whatever they thought as the number resolved on the screen, the year of waiting was about to end in a single small measurement, because a galaxy at the edge of the universe cannot move, and the question that had been held open, patiently, deliberately, for 12 months, was finally about to answer itself. We have arrived at the thing the entire story has been walking toward. In the next part, we find out what the picture showed. The dot had moved. Across 12 months of sky, the brighter of the two red points, bullet BD1, had shifted by about 49,000ths of an arcsecond. That is a motion so small you could never see it by eye, a motion that takes the angular precision of the most powerful infrared telescope ever built even to detect. But there it was. The cursor settled not on the old position, but a small, definite distance away from it, and a galaxy at the edge of the observable universe cannot land anywhere but exactly where it was. Galaxies, even relatively nearby ones, do not move across our sky in any way we can measure. A galaxy whose light has been travelling toward us for almost the entire age of the universe has, for all practical purposes, a motion of 0. This dot did not. The person moved the cursor to the second point, bullet BD2. It had moved as well, by about 24,000ths of an arcsecond, less than the first but still unmistakably, undeniably not 0. And both motions pointed in roughly the same direction, about 20 degrees east of north. The gap between the two dots had barely changed. They were moving together, across the sky, as a pair. In a single afternoon, with a single measurement, the meaning of the two faint red points turned over completely. The thing at the edge of the universe was not at the edge of the universe. The thing that had carried the perfect signature of the cosmic dawn, that had passed every test the dropout method could apply, that had sat behind the most powerful lens in the sky, looking exactly like the most distant objects ever found, was inside our own galaxy the whole time. It had been drifting slowly through the disk of the Milky Way, sliding across the sky year by year, while wearing the mask of the beginning of time. I want to let the strangeness of that settle, because it is easy to move past it too quickly. For a full year, two objects had been treated as candidates for the most distant things in all of creation, seen as they were when the universe was barely 100 million years old. And the truth, when it finally arrived, was that they were practically neighbours. The brighter one was moving sideways through space at about 116 kilometres per second, an ordinary speed for an object belonging to the thick disk of our own galaxy, the older population of stars that swims above and below the flat central plane. These were not visitors from the dawn of cosmic time, they were local. They had been here all along, hiding in plain sight in one of the most carefully studied fields in the sky, counterfeiting the farthest objects imaginable, and the only thing that gave them away was the one thing a galaxy can never do. They moved. Go back to that office for a moment and feel the shape of the realization, because it does not arrive the way discoveries arrive in films. There is no alarm, no shout, no dramatic music. There is a quiet room, a screen, two images laid one over the other, and a cursor. The person doing the measurement has done this kind of registration 100 times before, They line up the reference stars, the truly fixed points, until the two frames agree about where everything motionless should be, and then they look at the one thing that is not supposed to move, and it has moved. The first feeling is probably not wonder. The first feeling is probably doubt, the reflexive suspicion of any careful scientist, the instinct that says check it again, check the alignment, check for an error in the software, check whether some artifact is pulling the position. So they check, they run it again, they try it a different way, and the dot keeps sitting in its new place, a small stubborn distance from where it was a year ago, refusing to go back. And somewhere in that repetition the doubt quietly turns into certainty, and the certainty turns into something stranger, because the meaning of what they are looking at inverts under their hands. The thing they had half hoped was the edge of the universe is drifting through the neighbourhood. The record dissolves, and in its place appears something that is, in its own quiet way, just as remarkable, and a great deal closer to home. It is worth saying plainly what could and could not have produced that motion, so there is no doubt left. Nothing at cosmological distance moves across our sky in a year. Not the most distant galaxies, not anything at a redshift of 20 or 30, not anything whose light has been travelling for billions of years. Their apparent positions are frozen for all human purposes. The only things that shift measurably against the fixed background are objects close enough that their real motion through space translates into a visible slide across our view, and that means objects within our own galaxy, within at most a few thousand light-years. So a detected motion is not ambiguous. It is a one-word answer. It says near. It says local. It says, whatever these two dots are, they are not at the edge of the universe, and they never were. The proper motion did not merely favour the failed star reading over the galaxy reading. It closed the galaxy reading entirely. There was no version of the story left in which these were distant galaxies. The measurement had reached in and settled a year of patient uncertainty in a single afternoon. There is a particular feeling that comes with a result like this, and it is not disappointment, though you might expect it to be. The team had spent a year hoping, in some corner of themselves, for the galaxies, for the record, for the discovery that rewrites textbooks, and instead they got two failed stars in the neighbourhood. But sit with it for a moment, and the feeling turns into something closer to wonder. The most distant thing in the picture might also be the closest. That phrase, which had started as a nervous joke inside the team, which had become a working suspicion, had just been proven literally true, not as a metaphor, as a measured fact about the sky. The 2 points that looked like the edge of the universe were among the nearest things in the frame, and that is a stranger and in a way a more beautiful result than a record would have been, because it says something about the universe that a record never could. It says that near and far in our deepest images can look exactly the same. With the motion measured, the rest of the puzzle fell into place almost instantly. Remember the spectrum, the one that had come back 10 months earlier, leaning toward the failed star reading but not decisively. On its own, it could not choose. But combined with the motion, it no longer had to. The failed star interpretation, which had been holding on by a thin thread of slightly better numbers, suddenly had no competition at all. There was nothing else these objects could be. A galaxy does not move. A moving object is not a galaxy. And so the spectrum, freed from ambiguity, could finally be read for what it plainly was. The shape of the two dots' light was the shape of an ultra-cool failed star, its infrared glow carved by methane and water, its temperature low enough to belong to the very coldest category of object we know how to name. The thing at the edge of the universe was a cold, quiet, failed star, and its surface, as we're about to see, was roughly the temperature of a cup of tea left out to cool. The team wrote the paper. They gave it a title that told the whole story in a single honest line, describing two exciting distant galaxy candidates that had turned out to be two exciting, ultra-cool failed stars, and with that title, they were not only correcting their own result, they were raising a careful question about Capitaro and about a fraction of the most extreme distant galaxy candidates scattered through the literature. They were saying, gently but clearly, that some of what we've been calling the first galaxies may be something else entirely, wearing the same face. But before we widen out to what that means for the map of the universe, we should stay with the impostor a little longer. We should understand the exact trick of physics that let a cup of tea, drifting through our own galaxy, pass for the dawn of time, because that trick is the most quietly profound thing in this entire story. To understand what the team saw when they went back and read the spectrum with the motion in hand, We need to sit with a coincidence in physics, and it is the coincidence that makes this whole story possible in the first place. It is the reason a method that has been right thousands of times over 30 years was, for these two particular objects, quietly wrong. Two utterly unrelated kinds of objects, one at the very start of cosmic time and one in our own galactic backyard, leave essentially the same fingerprint in low-resolution broadband light. And I mean that almost literally. If you handed an astronomer nothing but the colours of the two dots across Webb's filters and asked them to say what they were, the honest answer would be that the colours alone cannot tell you. Let us take the two fingerprints and hold them next to each other. The first belongs to a galaxy at the dawn of time. Its light carries the Lyman break, that cliff carved by all the neutral hydrogen between the galaxy and us. Below a certain wavelength the galaxy goes dark, and above it the galaxy returns, and the expansion of the universe has dragged that cliff far into the infrared. For a galaxy at a redshift of 20, the cliff sits near 1 9/10 microns. For a galaxy at a redshift of 30, it sits near 2 8/10 microns. Webb samples the light in its broad filters, and a galaxy at these distances shows up bright in the filters above the cliff and vanishes in the filters below it. The second fingerprint belongs to a cold, failed star, and it comes from a completely different place. A very cold brown dwarf, in the coldest category we know, has an atmosphere ruled by molecules rather than the glowing gases of a true star. Methane and water vapour and ammonia float in its air, each absorbing light at its own particular wavelengths, and the combined effect of all that molecular absorption in an object only a few hundred degrees above absolute zero is to cut deeply into the object's light at wavelengths shorter than about 3 or 4 microns, while letting it shine through far more brightly between about 4 and 5 microns. The object stays faint in the shorter filters and then rises sharply in the reddest ones, and that rise, sampled in broad filters, has the same shape and sits in the same colours as the red-shifted Lyman break of a galaxy, at the edge of everything. Think about how deeply unrelated those two causes are. The first is atomic. It is hydrogen, the simplest atom there is, absorbing light across cosmological distances, acting on photons that have been travelling for more than 13 billion years. The second is molecular. It is methane and water in the atmosphere of a small, cool object, acting on light that has been travelling for a couple of thousand years. One is the largest scale imaginable, and the other is practically intimate. They share no physical mechanism whatsoever. The only thing they have in common is that, by an accident that no one designed and no one could have predicted, they bend the light at the same wavelengths. They are accidental homonyms in the language of the universe, two completely different words that happen to sound identical when you can only half hear them. And broadband photometry is exactly that, a way of only half hearing the light. When the team fit the spectrum of the two dots with a range of models, the failed star templates came out slightly ahead, and now, with the motion measured, that slight lead became the whole answer. The brighter object, Bullet BD1, best matched a surface temperature of about 350 degrees above absolute zero. The fainter one, Bullet BD2, matched a temperature of about 410 degrees above absolute zero. On the goodness of the fit alone, these were only marginally better than the Galaxy models, which is exactly why the spectrum could not settle things by itself. But the motion had settled things, and so the temperatures could be read plainly, no longer one option among several, but simply the truth about what these objects were. Let me translate those temperatures into something your body understands, because the numbers are the emotional centre of this whole story. 350 degrees above absolute zero is about 77 degrees on the Celsius scale, which is about 170 degrees Fahrenheit. That is the temperature of a cup of tea that has been sitting out on a counter for a few minutes. Still warm, still a little too hot to drink comfortably. A long way from boiling, a long way from anything you would call fiery. The brighter of the two objects, the thing that the most powerful telescope ever built spent a year trying to interpret as a galaxy from the dawn of time, has a surface roughly as warm as a mug of tea you set down and forgot about. The fainter one is hotter, about 410 degrees above absolute zero, which is around 137 Celsius, a bit hotter than a slow oven, above the boiling point of water, but not by an enormous amount. These are not the temperatures of the edge of the universe. These are kitchen temperatures. The most distant thing in the picture was the temperature of a cup of tea. There is something in that fact that should make you stop, and I want to give it room. Two completely unrelated physical processes, in two completely unrelated kinds of object, in two completely unrelated corners of the universe, are leaving the same mark in our best data. Hydrogen blanketing the light of a galaxy 90 or 100 million years after the beginning of time, methane and water absorbing the light of a failed star 1600 light-years away in our own neighbourhood. These processes do not know about each other. They do not resemble each other. And yet, by an accident of physics that nobody chose, the wavelengths line up, and the two become indistinguishable to a telescope sampling the light in broad strokes. This is the moment where the story quietly changes shape. The two dots stop being a puzzle to solve and become a fact to sit with. The universe speaks in a language that contains accidental homonyms, and even our finest instruments cannot always tell the words apart. Let me dwell on why the spectrum alone could not save us, because it reveals something honest about the limits of measurement. When the team spread the light of the two dots apart, they were using a low-resolution setting, which captures the whole sweep of colours at once but smears the fine detail together. At that resolution, the light of a cold, failed star and the light of a distant galaxy really do look nearly the same. The failed star's methane and water absorption blends into a broad rise, and the galaxy's hydrogen break makes a broad rise, and when you fit both models to the data, both fit. The numbers favoured the failed star, but only by a hair, the kind of margin that in a careful field is not allowed to settle anything. If you could have spread the light much finer, into a high-resolution spectrum the two would have separated cleanly, because the failed star's atmosphere carries distinct molecular bands, sharp signatures of methane and water and ammonia that a young galaxy's light simply does not have. But high-resolution spectra of objects this faint are enormously expensive in telescope time, sometimes beyond reach entirely. So the team was left with a low-resolution spectrum that leaned but did not decide, and a single other measurement that could cut through everything. Not a better look at the light, but a look at the motion. Not what the object is made of, but whether it moves, and that is the quietly profound thing. When the fingerprint itself is ambiguous, you stop asking the light what the object is and start asking the sky where the object goes. The answer was never going to come from the spectrum. It was going to come from watching. And so the two dots became a lesson, not only about themselves, but about looking itself. The boundary between near and far, between the dawn of time and the space just down the street, is not the clean wall the textbooks draw. It is softer than that, and stranger. And if you follow that thought a little further, it gets heavier than it first sounds. What it means is that some fraction of the most extreme distant galaxy candidates that have ever been catalogued in any deep field with any instrument may not be galaxies at all. They may be cold, local, failed stars that happen to share the fingerprint. The bullet cluster result was not a lucky one-off. It was a single clear example of a much more general property of the universe and of the limits of the kind of measurements we know how to make. What had always seemed like a clean separation between the far past and the local present turns out to be a little blurry at the very edge. Some of what we have been calling the first galaxies are nearby failed stars wearing the same spectral costume. And that costume is not a deception. It is not the universe trying to fool us. It is simply geometry and chemistry, the accidental architecture of how light and matter interact at these particular wavelengths. To really understand the imposter, and to feel how close it truly is, we have to stop treating it as a data point and start treating it as a place. We have to go and stand on one. Let us spend some real time with the object itself, because a brown dwarf is one of the strangest categories in all of astronomy, and there is a good chance you've never had the occasion to picture one clearly. A brown dwarf is, in the most direct terms, a failed star. To understand what that means, you have to understand how a real star is born. A star forms when a cold cloud of gas, mostly hydrogen with a little helium and a trace of heavier elements, collapses under its own gravity. As the cloud falls inward, the energy of that fall turns into heat, and the centre gets hotter and denser. If there is enough mass, the core eventually crosses a threshold, somewhere around 75 to 80 times the mass of Jupiter, where it becomes hot enough and dense enough to ignite steady hydrogen fusion. At that moment the object switches on. It becomes a true star, and it will spend millions or billions of years calmly converting hydrogen into helium and shining with the light of that reaction. Our sun is one of these. Nearly every point of light you can see in the night sky is one of these. A brown dwarf is what happens when the collapse falls just short. The cloud is too small. The centre gets hot but never quite hot enough to light the fire. The object that forms still holds a great deal of heat, left over from the energy of its own collapse, but it has no engine to replace what it loses. And so it does the only thing it can do. It cools. It radiates its warmth away into space over millions and then billions of years, dimming as it ages, drifting slowly toward the cold of the space around it. It is a star that almost was, glowing not with fusion but with the fading memory of its own birth. The boundary between a brown dwarf and a real, if feeble, star sits around 75 times the mass of Jupiter. The boundary between a brown dwarf and a very large planet sits lower, around 13 times the mass of Jupiter, below which the object never fused anything at all. These lines are somewhat arbitrary, and there is genuine debate about whether the way an object formed should matter more than its mass, especially now that the deeper surveys are finding free-floating planet-mass objects drifting alone in young star clusters, sometimes in pairs, belonging to neither category cleanly. But the essential idea holds. A brown dwarf is a failed star cooling alone in the dark. Astronomers sort these cool objects by temperature, using a sequence of letters that runs from the coolest real stars down through the failed stars to the very coldest known. The warmer failed stars glow in the red and infrared. As they cool, methane begins to dominate their atmospheres, the same methane that fills the air of Jupiter, and at the very bottom of the sequence sits the category called the Y-class, the coldest failed stars we know how to find, with surface temperatures below about 500 degrees above absolute zero. The coldest one ever found sits only about 7 light-years from Earth, and its surface is around 250 degrees above absolute zero, which is below the freezing point of water. It is, in a real sense, a star colder than ice, drifting almost next door. Bullet BD1 and Bullet BD2 belong to this coldest class. They are Y-class failed stars at the very bottom of the temperature ladder, which is exactly why their methane-carved light could counterfeit the edge of the universe. It is worth walking down that temperature ladder slowly, because the very existence of its lowest rungs is a recent discovery, and it is part of why this whole confusion could not have happened until now. The warmer failed stars, the ones just below the smallest true stars, were only recognized as their own category in the late 1990s. The next class down, defined by the appearance of strong methane in the object's light, the same methane that colors Jupiter, was named a few years later, in the early 2000s, and the coldest class of all, the one our two dots belong to, was only defined in 2011, based on a handful of frigid objects turned up by an infrared survey satellite scanning the whole sky. In other words, the imposters that fooled the dropout method were, as a recognized category, younger than the method itself. When the Lyman break technique was invented in the 1990s, the coldest failed stars had not yet been named. Nobody could have designed the method to guard against them, because nobody yet knew they were there in any number. The tools to study their spectra in detail only really arrived with that all-sky infrared survey, and then, most of all, with Webb. The contamination problem could not have been seriously studied before the data to study it existed, and that data is only a few years old. Consider, too, how slowly these objects surrender their heat, because it is the reason the coldest ones are so ancient. A failed star has no fire inside it. It has only the warmth it was born with, and it loses that warmth reluctantly, because the gas in its interior holds heat efficiently, and its surface is not large enough to radiate quickly. A failed star of modest mass takes something like 5 billion years just to cool below 500 degrees above absolute zero, and something like 10 billion years to reach the 300-degree range where our two dots sit. 10 billion years of cooling. The universe has only existed for a little under 14 billion, so a failed star at this temperature is nearly as old as everything, a slow-burning ember lit in our galaxy's early days and cooling ever since through the entire long middle of cosmic history. And the coldest one we have found so far, only about 7 light-years away, has cooled below the freezing point of water entirely, a surface colder than ice drifting almost within reach. These are not exotic distant curiosities. They are ancient, local, and common, and they have been keeping us company, unseen, the whole time. There is a further strangeness at the very bottom of this ladder that is worth naming, because it blurs an even older boundary, the one between a star and a planet. The deepest surveys have begun turning up objects with the masses of large planets that belong to no star at all, drifting freely through space, sometimes even paired with one another. Whether to call such an object a very small failed star or a very large rogue planet is, in 2026, a genuinely unsettled question, And the honest answer is that the categories our grandparents were taught, star and planet, neat and separate, do not carve nature quite as cleanly as we once believed. The universe fills in every gap it is allowed to fill, and the gap between the smallest stars and the largest planets turns out to be crowded with cold, dim, drifting things. Bullet BD1 and Bullet BD2 live in that crowd. They are ordinary members of a population we are only beginning to map, and their ordinariness is exactly what makes them important. Here is the part that gives these objects their strange dignity. Because a brown dwarf cools so slowly, the coldest ones are extraordinarily old. To cool all the way down to 300 or 350 degrees above absolute zero, a failed star of modest mass needs to have been radiating its heat away for something like 10 billion years. 10 billion years. The universe is only about 13.75 billion years old. So an object at that temperature today is essentially a fossil, a relic of an early chapter of our own galaxy's star formation. Something that has been quietly cooling since a time before the Sun existed, before the Earth existed, before there was a solar system at all. The cold failed stars in our neighbourhood are, in a real sense, among the oldest objects we can study up close. Each one is a small, dim record of what our galaxy was like in its youth. Bullet BD1 has been cooling alone in the dark for longer than the ground beneath your feet has existed. Now let me try to take you there, because I think it is the only way to really feel how close and how strange this object is. Imagine you could stand somewhere on Bullet BD1. It does not have a solid surface the way a rocky planet does, but imagine you could find yourself at the boundary where its atmosphere begins to thicken into its interior. The air around you is dense and dim, tinted a brownish grey by methane, thick with water vapour and traces of ammonia. High above, in the coldest upper layers, ammonia freezes into thin, drifting streamers of ice, and water condenses into clouds, though not clouds like any you have seen, forming at pressures and temperatures with no match anywhere in your experience. The sky above you is dark. There is no sun. There is no nearby star to light it, because this object drifts entirely alone through interstellar space, with no companion to orbit and no warmth arriving from outside. The only light is the object's own, a dim infrared glow rising from below, the last of its ancient heat leaking slowly away into the cold. On your skin, if you could somehow be there, the temperature would be about 350 degrees above absolute zero, roughly 77 degrees Celsius, the warmth of a cooling cup of tea. The air would feel warm and humid, almost tropical, but in a sealed, sunless dark rather than under any sky you know. Beneath you, the gravity would be crushing, several times what you feel on Earth, holding you hard against whatever passes for the ground. You could not stand, you could barely move. You would only feel the warm, heavy gas, the dim glow from below, the cold dark pressing down from above, and the slow churn of heat rising and falling as the object stirs its own atmosphere. There would be no horizon in any familiar sense. There would be no sunrise ever. There would be no one, and there never was. This object has been drifting through the disk of the Milky Way, cooling by itself for 10 billion years, and it will go on cooling for 10 billion more, until its methane freezes out of the air as a kind of snow, and its atmosphere thins toward a rigid stillness, long after the sun has swollen and died and the Earth is gone. Stay on its surface one moment longer and consider its solitude, because the loneliness of an object like this is difficult to hold in the mind. It has no star. It has no companion, most likely, no planets, no system, nothing bound to it and nothing it is bound to. It simply falls through the emptiness between the stars alone, as it has for 10 billion years, radiating the last of its birth heat into a dark that will never warm it again. Nothing has ever landed on it. Nothing has ever looked up from it. In the entire history of the universe, until a telescope 1.5 million kilometers from Earth happened to catch its faint glow, no one and nothing had ever taken any notice of it at all. And it will go on that way, indifferent and unbothered, long after everything you have ever known is gone. There is something almost tender in that, and something humbling. This object owes us nothing, knows nothing of us, and yet for one strange year it stood at the centre of a question about the beginning of time, simply because its cooling light happened to fall in the same colours as the dawn. It played the part of the edge of the universe without ever leaving our own galaxy, and then, with one small sideways step across the sky, it handed the part back. This is what was hiding in the bullet cluster field. Not a gathering of billions of stars from the first 100 million years of time. something far closer and far quieter, a single failed star drifting alone through our own galaxy, about 1,600 light-years away, casting its dim infrared light across the dark toward Webb. And by another accident of coincidence, its light happens to carry a signature that resembles the stretched-out break of the most distant galaxies we can imagine. From the outside, in our broad filters, the two are nearly identical. From the inside, they could not be more different. And here is the thought that should stay with you. Bullet BD1 and Bullet BD2 are not rare. They are not lucky finds. They are typical. Our galaxy is quietly full of these cold, failed stars. Deep surveys have begun turning them up in 2s and 3s and dozens in the very same fields meant to catalogue the first galaxies. The estimates now run to tens of millions, perhaps hundreds of millions of these failed stars drifting through the Milky Way, a hidden population that no telescope before Webb could have systematically found, because the objects are too faint and too cold for anything less sensitive to see. The galaxy you live in is, in part, a galaxy of failed stars. They have been here the whole time. They have been here longer than the Sun, and we are only now, for the first time, beginning to notice them. What that does to our map of the universe is the last thing we need to understand. Let us ask the question that the two dots really opened up, which is not about two objects at all, but about the whole population behind them. How many of these things are there? How many cold failed stars are drifting through our own galaxy, sitting in the deepest images we take of the early universe, quietly pretending to be galaxies at the edge of time? The answer has been coming together through a parallel effort, a survey designed to catalogue the first galaxies that has, almost as a side effect, become one of the best tools we have for finding the hidden failed stars mixed in among them. The numbers are worth hearing slowly. In a careful study of two of the deepest fields we have ever imaged, one team identified 41 failed star candidates, most of them in the warmer methane class and 10 of them in the very coldest class, the same class as our two dots. From how densely these objects appear in those small deep patches, you can estimate how many there must be across the whole sky. The coldest ones show up at a density of roughly 1 every 50 square arc minutes. The warmer ones are about 5 times more common. There are about 150,000 square arc minutes in the entire sky. Do that arithmetic and you get something on the order of 3,000 of the coldest failed stars and perhaps 15,000 of the warmer ones, bright enough to be caught in surveys this deep. And that is only the ones we could currently detect. The true population, including all the ones too faint and too cold for even Webb to see, almost certainly runs to tens of millions, perhaps hundreds of millions. The total number of failed stars in the Milky Way may well rival or exceed the number of ordinary low-mass stars. Sit with that for a moment, because it quietly rewrites something you were probably taught. The picture of the Milky Way as a gathering of a few 100 billion stars is not wrong, but it is incomplete. Alongside those stars drifts a second population, comparable in number, of objects that did not quite make it to starhood, that have been cooling in the dark for billions of years, scattered through the disk, dim enough that no telescope before this one could find more than a handful of the nearest. The failed stars are not a small curiosity at the bottom of the list. They may be among the most common objects of their kind in the entire galaxy. And what that means for our story is simple and important. Bullet BD1 and Bullet BD2 were not a fluke. They were typical. There are almost certainly thousands more like them sitting in deep field catalogues right now, waiting to be sorted out, some of them very likely still labelled as distant galaxies. So what we have witnessed, when you look at it clearly, is the dropout method being audited honestly, in real time, by the very people who rely on it. And I want to be careful and fair about what that audit found, because it is easy to tell this story as a scandal, and it is not one. The method works. It has worked for 30 years. It has found thousands of genuine distant galaxies across survey after survey. The Lyman break technique is not broken. What the community has learned is that the method, like every tool in science, has an edge case, a place where it can be fooled, and that edge case is the population of cold failed stars whose light happens to overlap the signature of the earliest galaxies. When the method was first invented, it looked for galaxies at modest distances, where the break sits in the ultraviolet, far from any wavelength where a failed star could interfere. The coldest classes of failed star had not even been discovered yet. There was no way to anticipate the problem, because the objects that cause it were unknown. But as the method reached to greater and greater distances over the decades, The break it was hunting for slid deeper into the infrared, and by the time Webb was chasing galaxies at redshifts of 15 and 20 and beyond, that break had moved into exactly the same colours where a cold, failed star's methane and water absorption lives. The collision was inevitable. It was not a mistake anyone made. It was two frontiers, the search for the first galaxies and the discovery of the coldest failed stars, arriving at the same patch of the spectrum at the same time. And the response of the field, once the problem became clear, is the part that should make you trust science more, not less. The community did not hide the contamination. It did not bury the awkward reclassifications. It published them openly, including the most spectacular cases, even when doing so meant walking back a claimed record. The Bullet Cluster paper, with its plain and slightly rueful title about exciting galaxies turning out to be exciting failed stars, is exactly that kind of honest correction. The exciting galaxies were genuinely exciting. They turned out to be failed stars, and the failed stars are in their own way even more remarkable because they reveal a hidden population in our own neighbourhood that no earlier telescope could have found. The story did not get smaller when the galaxies turned out not to be galaxies. It got differently large. There is one corner of this story that is still open, and honesty requires that we return to it. Capitaro, the object that started all of this, the previous most extreme candidate, has still not had its decisive motion test completed. The photometric evidence leans toward the failed star reading, the same way the bullet dot spectrum did before the motion settled them, but leaning is not proving. 3 interpretations technically remain on the table. It could still be a galaxy at a redshift of 32, the most distant object ever seen. It could be a cold, failed star, like our 2 dots. Or it could be the rare, never-yet-confirmed explosion of a very massive early star, seen at a middling distance and stretched out in time. The measurement that will decide is the same one that decided the bullet dots, a precise look for motion over a long enough baseline, and it is expected to arrive by late in 2026. The community is waiting. Somewhere, a team is preparing the observation right now, and when the second image finally comes down and is laid over the first, the pixel that holds Capitaro will either sit exactly where it was, or it will have slid a little to the side. If it has not moved, we are looking at something extraordinary, either a galaxy from the dawn of time or the first directly detected death of a primordial giant. If it has moved, we are looking at another cold failed star that fooled us for years. Both answers would teach us something. Only the measurement can choose. Step back now and look at what all of this does to the map. Astronomers build their sense of cosmic distance like a ladder, each rung calibrated against the one below it. The nearest rungs are rock solid. The shift of a nearby star against the background as the Earth swings around the Sun gives direct distances to the closer stars. Certain kinds of stars and certain kinds of exploding stars serve as standard markers that extend the ladder across enormous gulfs. The stretching of light from distant galaxies carries the ladder out to the edge of what we can see. Each rung leans on the last, and the whole structure has been refined for a century, so that the distances to most objects in the sky are known well. What the bullet cluster failed stars reveal is that one of the ladder's oldest assumptions, that we can cleanly tell a nearby object from a distant one, has an edge case at the very top. Almost always the distinction is obvious. Foreground stars look like foreground stars. Background galaxies look like background galaxies. But the coldest failed stars, at the edge of the distant galaxy catalogues, are not obvious. They sit in the same fields as the real early galaxies, they make nearly the same mark, and they can be told apart only by measurements that take years to gather. The top rung of the ladder, in this one corner, has a fog around it, a haze of nearby objects that mimic the farthest things in the sky, and the only way to see through the fog is the slow, patient work of taking a second look and watching for motion. I want to be precise about how narrow this fog really is, because it would be easy to overstate it, and overstating it is exactly the error the fringe voices make. The contamination is small. The best current estimate is that only about 1 in 1,000 of the deep field candidates for distant galaxies turns out to be a cold failed star. 1 in 1,000 sounds like almost nothing, and in a sense it is. But now remember how many candidates there are. The deepest surveys have produced tens of thousands of them. 1 in 1,000 of tens of thousands is still tens of objects, tens of cases where the most distant thing in a catalogue is really one of the nearest, tens of small false records scattered through the literature, and the rate is not even across the board. It climbs for the very most extreme candidates, the redshift 30 and beyond, and it climbs in the parts of the sky where our galaxy's failed stars are densest. So the fog is thin, but it gathers exactly where we are most tempted to plant a flag, at the far edge, on the most spectacular claims. That is what makes it dangerous out of proportion to its size. It is a small effect that lives precisely in the place where a small effect can rewrite a headline. And here is the reassuring counterweight to that, the part worth holding on to. The genuine records survive. The most distant galaxies that have been properly confirmed with real spectra and real cross-checks remain exactly where they were at redshifts around 14, seen when the universe was under 300 million years old. Those are real. They are still surprising, still bright and abundant enough to keep galaxy formation theorists busy and honest. And that surprise is one of the legitimate live questions in the field. Nothing about the failed star discovery erases them. What the discovery erased were the most extreme claims, the ones that reach past the confirmed records into territory where galaxies should not yet exist, and those were exactly the claims that most needed a second look. So the cleanup does not shrink the early universe, it sharpens it. It separates the real frontier, which is genuinely astonishing, from the false frontier, which was a fog of cold local objects all along. The map is not smaller after this, it is more honest. Here is the gentlest and most important thing to take from all of it. The strangeness did not disappear. It moved. For a while it looked as though the early universe itself was breaking the rules, producing galaxies too soon, too bright, too grown up for the time available. Some of that tension was real and remains genuinely interesting, but some of it, the most extreme part, the redshift 30 and beyond, is quietly dissolving as those candidates are revealed to be cold failed stars in our own galaxy. The universe is not broken. The models are doing better than they seemed to be 2 years ago. What has happened is that a piece of strangeness we had assigned to the unreachable edge of time turns out to live, instead, about 1600 light-years from the Sun. The Milky Way holds failed stars old enough to approach the age of the universe, cold enough to counterfeit the dawn of time, and abundant enough to salt the deepest catalogues we own. The strangeness is not gone. It is closer. It has been closer the whole time. We simply had not yet looked carefully enough to see it. And that, in the end, is a more comforting universe than the one we thought we had, though it takes a moment to feel why. Sit with this the way only someone listening late at night can sit with a thought. 350 degrees above absolute zero, the warmth of a cup of tea left to cool on a windowsill. The most distant object the most powerful infrared telescope ever built, pulled out of the bullet cluster field, turned out, when we finally looked closely, to be the temperature of something you could nearly hold in your hands. The most extreme galaxy candidate in one of the most carefully studied images of the early universe was cooler than the inside of a car on a summer afternoon, barely warmer than the water in a kettle just beginning to steam. The record we almost claimed was a mug of tea drifting through the dark, and it is close. About 1600 light-years, which sounds like a great distance until you set it against the thing it was pretending to be. 1600 light-years is roughly the distance to the Pleiades, the little cluster of stars you can see with your own eyes on a clear winter night, the seven sisters that have hung in human stories for thousands of years. It is nearer than the great nebula in Orion. It is almost nothing compared to the span of the galaxy, and it is less than nothing compared to the edge of the universe. The light from Bullet BD1 crossed 1600 years of space to reach Webb's mirrors. The light from a genuine galaxy at the edge of time has been travelling for more than 13 billion years, a journey 10 million times longer. And yet, in our broad filters, the two arrived looking like twins. The boundary between the almost here and the almost unreachable, the boundary we have drawn as a clean line for a century, turns out to have a fog of tea-warm objects hanging in front of it. And it is old. We cannot measure its age precisely, but the temperature is a kind of clock, because a failed star cools at a rate set by its mass and its birth. To have cooled all the way down to the warmth of a cup of tea, Bullet BD1 must have been radiating its heat into the dark for something like 10 billion years. That is older than the Sun, which is about 4.5 billion years old. It is older than the Earth. It was already cooling toward the temperature it holds today for billions of years, before the ground beneath your feet had gathered itself out of a disk of dust around a young yellow star. It has drifted through the disk of the Milky Way, at the steady speed of the old thick disk population it belongs to, for as long as our galaxy has looked anything like it looks now, and it will go on cooling, alone, in the cold and the dark for billions of years more, long after the sun has burned through its fuel and swollen and shrunk to a dim ember, long after the Earth is gone. Bullet BD-1 will outlast all of it, quietly losing the last of its heat, drifting through whatever the galaxy becomes. This is the object the most powerful telescope ever built mistook for the most distant galaxy ever seen. And there is a strange dignity in that, because the object is not less remarkable for failing to be a galaxy. It is more. It is a fossil of our galaxy's youth, cooling toward the temperature of the space around it, sitting in our own neighborhood, having been here the whole time. The universe contains objects this strange, and they are not far away. They share our corner of the galaxy. They were here billions of years before any of us, before the sun, before the Earth. The lesson is not that the method was broken, because it was not. The lesson is not that cosmology was broken, because it was not. The lesson is that the universe sometimes speaks in accidental homonyms, and the work of astronomy is to learn to tell the words apart. Two completely unrelated kinds of object produce the same fingerprint in our best data. One sits at the edge of everything, the other sits in our backyard, and from the outside they look the same. Two answers from the same fingerprint. We introduced that phrase back when we were looking at how the dropout method works, and by now it has grown into something larger than a note about technique. It has become a fact about the act of looking itself. Our finest instruments, at the very edge of what they can measure, produce data that cannot always separate two utterly different objects. The methane break of a cold failed star and the stretched hydrogen break of an early galaxy are the same word spoken in two languages, and only a second, more careful listening can tell which language is being used. That second listening is the measurement of motion, the higher resolution spectrum, the patient template fitting that includes the imposters. These are not new tools. They are the ordinary instruments of careful work. What is new is that we have learned they are sometimes necessary even for the most extreme candidates in the deepest fields, because two answers really can come from the same fingerprint, and only the extra care tells us which answer is right. So the next time you see an image of the early universe, in an article or a book or a film, and a bright point is labelled the most distant galaxy ever found, hold the bullet cluster in your mind for a moment. Remember that two of the most exciting distant galaxy candidates of their year turned out to be cold failed stars in our own galaxy, cooler than a kitchen oven, older than the sun, drifting quietly through the disk. Remember that the object that started it all may turn out the same way when its own motion is finally measured. Remember that the map of cosmic distance has a soft, foggy region at its far edge, and that the only way to clear the fog is the slow, patient work that this team modelled for the whole field, when they held a record in their hands and set it down for a year to be sure. Now let me leave you where this story wants to end, which is outside, under a dark sky. If you go out on a clear night, far from the city lights, you will see thousands of stars with your own eyes. You will see, if you know where to look, the pale band of the Milky Way arching over you. You will see, if the sky is dark enough and you are patient, the faint smudges of a few distant galaxies. But what you will never see, with any telescope you could buy, with any glance you could take, are the failed stars. The tens of millions of cold, dim objects drifting through our own galactic neighbourhood, cooling silently in the dark, invisible to nearly everything. Webb catches them in 2s and 3s in the deepest images ever taken. Most of them are too faint even for Webb. The galaxy is full of quiet things that we cannot see, that we have been overlooking for as long as there have been astronomers, and the two dots in the bullet cluster are only a small reminder of how crowded and how quiet our galaxy really is. The cosmic web above your roof, right now, holds an enormous number of these cold, dim objects that even the brightest telescopes ever built can barely detect. Some of them, at this very moment, are sitting in careful catalogues labelled as the most distant galaxies ever found. Some of them will be sorted out in the coming years by the same patient combination of spectrum and motion that resolved the bullet dots. Some of them will drift on undetected, adding their faint light to images that are supposedly about the dawn of time but in fact carry quiet local things mixed in. The map has, in this one corner, a small and permanent uncertainty, one we can only ever reduce, never quite erase, because the physics that makes the imposter is the same physics that makes light itself, and no amount of care will change how methane and hydrogen happen to bend the light at these particular wavelengths. The most distant thing in the picture might also be the closest. That phrase began as a nervous joke in a small office, and it has become, by the end of this story, a true statement about the structure of our deepest images, and maybe about looking itself. Some of the dots we call the first galaxies are ancient, cold fossils inside our own neighbourhood. They are not at the dawn of time. They are not at the edge of the observable universe. They are drifting through our own galactic disk, having done so for as long as the sun has existed and longer. The picture of where the universe begins and where our galaxy ends is softer than the textbooks suggest. The boundary is not a wall. It is a fog of quiet things, wearing the faces of louder, farther things, and it is made in part of the failed stars of our own galaxy's history, cooling toward a stillness they will not reach for billions of years. The Milky Way is, in part, a galaxy of failed stars. They have been here the whole time. They have been here longer than the sun, and they will be here long after the sun is gone. Some of them are visible to the most powerful telescope we have ever flown. Most of them are not. They drift slowly through the disk, doing nothing, needing nothing, cooling in the dark, our quiet companions in this corner of the galaxy, even though they will never know we are here, and we will, for the most part, never notice them. So when you look up tonight, let the picture in your head be a little softer at its edges than it used to be. Some of the dots you can see, and some of the dots you cannot, are not what they appear to be. There is one last thing worth carrying with you as you drift, and it is the gentlest version of the whole story. We did not lose the early universe in all of this. The cosmic dawn is still real. The first galaxies are still out there, still being found, still being confirmed one careful spectrum at a time. What changed is only that a few of the objects we had been most excited about, the very most extreme ones, turned out to be near instead of far, cold instead of ancient, familiar instead of impossible. And the method that found them, the beautiful old trick of reading distance from a missing colour, is not broken by any of this. It has only learned a new humility, learned to ask of its most extreme finds a second quiet question before it celebrates. Does it move? That single question, cheap to ask and impossible to fake, now stands guard at the far edge of the map, sorting the true frontier from the fog. So the universe you're settling into tonight is not a smaller one. It is a more honest one, and in some ways a warmer one, because the strangeness we thought lived only at the unreachable edge turns out to be scattered close around us too, drifting quietly through our own galaxy, older than the sun, cooler than a cup of tea. The most distant thing in the picture might also be the closest. The galaxy is full of quiet things. They are not going anywhere. Sleep well.